All right, so we started section 3.3 last class period. We're taking a look at increasing and decreasing functions and the first derivative test. So just as a reminder, increasing and decreasing have these definitions. It talks about what happens if you move sort of from left to right on the graph. If you're moving from left to right and the y value is smaller on the left and bigger on the right, it's increasing. If it's bigger on the left and smaller on the right, it's decreasing. And then we talked about what that means in terms of a derivative itself. So if a graph is increasing, like this first one with the blue on here, it means that that blue is a tangent line there, and that tangent line would have a positive slope. So when I've got an increasing graph, I have a positive derivative. That's the first statement. And the second one is the reverse of that. If I have a decreasing graph, then I have a negative derivative. So that's the second picture here with the red line that's coming down. So if the graph is decreasing, then the graph has a negative derivative and vice versa. And then the third one says that if the derivative is zero on an interval, not just at a point, but on an interval, then we have a constant graph. We don't see number 3 happen all that frequently. Most of our graphs have a changing nature to them. They're increasing, they're decreasing, and sometimes multiple pieces of that going on. And then we talked about the first derivative test, which is kind of the big point of this particular section. The first derivative test says the following: if the graph changes from increasing to decreasing or decreasing to increasing, then we will have a local maximum or a local minimum. And another phrase for that is a local extrema. And we had seen that before, or relative extrema. We saw that back at the beginning of chapter 3. I didn't make mention of this. I did. I remember doing it in this class about the idea that the local or the relative extrema has to do with what's happening in a nearby value or nearby point, or sometimes we call it a neighborhood. And then the third one is that if the signs don't change, then we don't have a local extrema. Okay, so if the derivative itself has the same signs, that should say f prime. That is a typo. If f prime has the same sign, then f of c is not a local extrema. Okay, so we had done one example you guys had mentioned. And so the process by which we do this is the same process every time. We find the derivative, we set it equal to 0 or does not exist, and we find those potential locations where it might have maxes and mins. So on this one, when we took the derivative, set it equal to 0 and equal to does not exist, we found 3 values. Equal to 0, it was equal to the 2 and the negative 2 down here. These are 2 places that the derivative is 0. And then the derivative does not exist if the denominator here we're being is 0, so that's an x equals 0. So these 3 points end up getting placed on a number line, right? Negative 2, 0, 2 in order. They don't have to have any perspective, like it doesn't matter how far apart they are or anything like that. But what I want to test is I want to test the points that are in between them. We know what happens at those values. The derivative is 0, or it doesn't exist. What I want to know is what happens in between them, these intervals. Are the interval locations increasing or decreasing? And they have to be one or the other, because they're not 0. We found all the locations where they're 0 and does not exist. The only other options are positive and negative. So we want to find out where they're positive and negative, and those positive and negative locations tell us where it's increasing and decreasing. And then, while this question did not ask it, we could have been asked with this exact same question, what about the relative extrema? So if you notice on this first one, it's positive and it's negative, right? Increasing and then decreasing. So there is a location right here at negative 2 where I have a maximum, right? It is going to be a maximum in that location. Now at 0, it's the decreasing. Nothing's happening there in terms of maxes or mins. But then on the third one over here, it's decreasing and then increasing. There is a relative minimum right here. Okay? Now, can you check all of this by simply looking at the graph? And the answer is yes, you can. It's not always easy to get the exact locations where that's happening though, right? And so that's what the first derivative test does for us, is it finds those exact locations where it's changing from increasing or to decreasing or vice versa. Okay, so let's do another example. Directions stayed the same. It's not asking us for maxes and mins yet still, but it is asking us where it's increasing and decreasing. And it is a trig function, right? Or at least a couple of them, in fact. And we're supposed to be identifying whether it's increasing or decreasing. So again, the process is always the same. Jot it down if you'd like. I'll write it on the screen since we haven't done this in a bit. So our first step is always to find the derivative. Okay? All right, I'm writing really small today. Let's write a little bit bigger so you can read it. So find the derivative. The second step is to set the derivative equal to 0 and does not exist. It's always our second step. The third step is that, and these create critical points, or critical values, we'll say, is to put, we're going to put our critical numbers on a number line. So we put our critical numbers on a number line, and we test between. These are the same steps every single time. Doesn't matter if I have an algebra function, which I did on number 1, or if I have a trig function on number 2, or if it's a combination thereof. It could be a combination of those two things too. So these are our sort of bulleted list of things we're going to do. So the first thing we're going to do is we're going to find a derivative. Now, as mentioned last time, the derivatives in chapter 3, not just last time, but multiple times throughout this chapter already, the derivatives in chapter 3 are typically a little bit more straightforward than the ones we did in chapter 2. That doesn't mean you don't have some product rules and chain rules and things, because you very well might, and in fact we do here. This has cosine squared. So another way of rewriting this in a way that's a little bit more helpful to see what's happening is that the cosine function is being squared, and because you have something inside that's not just x that's being squared, you're going to have a chain rule, right? You have an inside function and you have an outside function. So the chain rule says I take the derivative of the outside, which means I bring the 2 down. I rewrite the inside, and I decrease the degree by 1. And then I need the derivative of the inside. So what is the derivative of cosine of x? Negative sine of x, yes. That's the first piece, right? It's this piece's derivative. Now I need the derivative of negative cosine x. Well, we kind of just found the derivative of cosine of x. So the derivative of cosine of x was negative sine x, so the derivative of negative cosine of x would be positive sine of x. Is that okay for everybody? There's really not a whole lot of cleanup to do. If you would like, you can certainly move the negative that's attached to the sign to the beginning, or maybe you would have written it that way already when you were working through it. So the best option we can do really here in terms of cleanup is to just write it like this. If you want to write sine in front of cosine instead of cosine in front of sine, you could change the order of that. That doesn't make it any simpler. But this is as clean as it gets. Okay, so that's step 1. We found the derivative. Step 2 is to set it equal to 0, does not exist. Now, sine and cosine functions always exist. So there is no does not exist with those. If I were dealing with tangent, then I would look for it where it doesn't exist, right? So all the trig functions have these properties. We've talked about them. Tangent, cotangent, secant, and cosecant all have asymptotes, but sine and cosine don't. So there's no does not exists. The only thing that we can work with on this is where it's going to be equal to 0. Right? I'm looking for where it's equal to 0. So I'm going to take my negative 2 cosine x sine x plus sine x and set it equal to 0. Now, you might be tempted to say, let's move something to the other side and then simplify. And I understand that sort of feeling. We do that with linear equations all the time, right? If this had just said, x squared plus 3 equals 0, that's not even linear, but it only has one x in it, then yes, it would make sense to separate things and so forth. But both pieces of this, and by pieces I mean this piece and this piece, have a variable in it, right? So I don't want to throw something on the other side and try and sort of divide something out. That will lose values. I don't want to do that. What that means is that I'm at the same point that I am if I've got like a quadratic equation. I have to do something with factoring. So as you take a look at negative 2 cosine x sine x and then plus sine x, what can you factor out of both pieces? Sine x. It's what they have in common, right? So we're going to pull out a sine of x, which leaves me with negative 2 cosine x and then plus 1. Don't forget the plus 1. That's a common thing to forget. But if I factor it out, it's like dividing, right? If I take sine x and I divide a sine x out, I'm left with 1. And then just like with factoring with quadratics, we take each piece and we set it equal to 0 and solve. So we're now going to be looking for where sine of x is equal to 0 and where negative 2 cosine x plus 1 is equal to 0. Okay, so sine x is equal to 0. And I didn't mention this, and I should have. Let me draw your attention back up to this. They give us an interval that often happens when we're dealing with trig functions because of the repetitive nature, right? They're cyclic. They keep doing the same thing over and over again. You get infinitely many solutions. We're usually not interested in calculus on the infinitely many solutions perspective. We do that in trig, and we focus on that a little bit more there. But we typically see an interval when we're working with this in calculus. So we're only looking at the interval from 0 to 2 pi. That's one trip around the unit circle, right? Or it's one rotation of, or one period, if you will, of your sine function or your cosine function. So whether you're thinking unit circle or whether you're thinking graph, either one's fine. We need to know, where does the sine of x equal to 0? What angle measures does that happen? Do you know? Do you remember? I'll draw a unit circle if we need to. Somebody give me a guess. Okay, at 0, this is a sine, this graph, or this where this green point is where I plotted, is a location where the sine graph will have a 0 or an x-intercept. What else? Pi. Over here. And then back at 2 pi, right? It's going to keep hitting on the left and the right-hand side. And if you remember, sine values are the y values in terms of the ordered pairs of those locations. So those are the two locations on the unit circle where I have a y value of 0. Now, I'm going to list the 0 and the 2 pi, though they're technically not in my interval. They're the endpoints already, right? And they're not really included. But they're going to cap the ends of what I'm going to be doing anyway. So I'm just going to list them right now, even though they're not really on my interval. They're the endpoints of my interval. All right, the other piece I need to solve. So I'm going to move the 1 to the other side, so subtract 1. If I divide by 2, negative 2, this will give me negative 1 divided by 2, negative 2, which is positive 1/2. Now I need to figure out where the cosine values are equal to 1/2. So let's think quadrants first. What quadrants give me positive values for cosine? Going to be 1, because 1 gives me all values that are positive, and 4, yeah. So these are our two locations where my cosine values are going to be positive. Now I need my cosine value to be 1/2. Okay, well, 1/2s occur either here or here, right? These are the two spots. One's at a pi over 6 value and one's at a pi over 3 value. Which one's the right one for cosine to be 1/2? How do we know?
Because it's close to the x.
Okay, it has to do whether it's close to the x-axis or the y-axis. So on these locations, one of them, let me move my one. One of them is closer to x and one of them is closer to y. So let's just list the ordered pairs and then we'll figure out which one it is the one we want. So let's do the ordered pair on the lower one first, right? The pi over 6 one. There's going to have a 1/2. Is the 1/2 in the location for x or is it in the location for y? It's y. Good. And so over here, this one's x. And we could write in the square root 3 over 2, but I don't really care about that right now. I need something that's going to be 1/2, right? Okay, so which one's cosine? Is cosine the x value of 1/2 or is it a y value that gives me 1/2? It's the x. So this is the location that I actually need to answer the question for cosine of x equal to 1/2. Is that happening at pi over 3 or at pi over 6? That one's pi over 3. Okay, so even if you don't remember it, you can reason through it and do that way. There's another way you could do this too. Let me show it to you real quick. So what do we say? Pi over 3, right? I need one more value, which we'll get in a second. The other thing that you could do is you could say, okay, well, I know it's pi over 3 or pi over 6, right? I know it's one of those two. Couldn't you just take your calculator and let your calculator tell you which one it is? Of course you could. You could type in cosine, pi over 6, and it's either going to spit out 1/2 or it's not. Yeah? use the technology to your advantage. I mean, it's not cheating. You have it to be able to use, right? So if you're having trouble remembering, especially in a timed and kind of an environment or something like that, then there's no reason to have to stress about this and to get the wrong one. Agreed? There's just not. It is pi over 3. I also have this value down here, which, these are terribly unstraight lines, which if I go this direction would be negative pi over 3, but I don't want to go that way because I'm supposed to be getting a value between 0 and 2 pi. If I went around the circle this way, do you know what it would be? What is it? 5 pi over 3. Yeah, it's 5 pi over 3. Okay? And if you're not sure, or you're not thinking like, how did we get 5 pi over 3? You can also just take 2 pi, which would be going all the way around, and go backwards pi over 3. So if you took the number 2 minus 1/3, which is 2 pi minus pi over 3, you get 5 pi over 3. So this is our second piece, 5 pi over 3. Okay, I technically only have 3 critical values. I have the pi over 3, the 5 pi over 3, and the pi. The reason I say that I don't really have the 0 and the 2 pi is because those are my end values anyway. So as we go into step 3, we're going to put our critical numbers on a number line. I'm going to put them over here because I have a little more space. I have the ending values of 0 and 2 pi. Everybody agree with that? They told me that. So, and they're showing up in the sign values too, but they told me that. I just need to make sure I get the other ones on there in order. Which one comes first of the 3 that are highlighted in purple? Pi over 3. And again, it doesn't matter how far we space them apart, so you might as well just make them whatever works for you. What's the next one? Pi, and then the last one would be 5 pi over 3. So these are my values. I want you to take your calculator, because you can use your calculator to help you with this. Okay, so if you really want to use unit circle values and find what happens at cosine at negative 2 cosine x sine x plus sine x at each one of the unit circle values you choose, you could do that. That is not the easiest approach here because that's not a simple, it's not just sine of x, right? I don't know just all those values all multiplied together in a quick fashion. What I would like for us to think about is what values these are approximately. Pi is about 3.14. Y'all know that, right? Pi Day happened recently. Did you know that? Yeah, it did. So pi is about 3.14. So if I took pi and I divide it by 3, what really close whole number value am I going to get? It's close. It's almost 1, right? So this value is almost 1. Oops, I wrote it underneath the wrong one. Sorry. This value is almost 1. Agreed? Yeah, I mean, it's close. It's close enough for what we're talking about here. Pi is about 3. And if you're not sure, somebody type in what 5 pi over 3 is for me and tell me some sort of a nice-ish value that it is. It doesn't have to be a whole number. It could be like a decimal point something too. It's fine. What is it about?
5.2.
5.2. Wonderful. That's great. What I want values that are in between 0 and 1, 1 and 3, 3 and 5.2, and 5.2. Oh, and I didn't have you write it down. This is 0, of course. This is 6.3. I mean, approximately 6.28, right? I need values that are in between these. So we might as well choose some nice values in between them. What would be nice-ish between 0 and 1? Maybe a half, right? I mean, is that okay? I'm going to do mine in blue. What nice value would be between 1 and 3? Well, 2 would. Yeah, of course. How about between 3 and 5.2? 4 or even 5 if you wanted, right? And how about between 5.2 and 6.3? Probably 6. Okay, these blue values that I have written in, I'll circle them too, are the values that I want to test in my derivative. So take your calculator, and I want us to put in the derivative that we found, and any of the versions of it are fine. I'm going to do the one where I pulled the negative to the front just because it's a little bit easier to write it in without parentheses everywhere. So I have negative cosine of x, sine x, and then plus sine of x. I put my derivative in. I'm always testing this in the derivative. And maybe I should highlight that, not highlight, but write that in here. Test between. And this is in the derivative, right? I'm doing it in the derivative equation. So you got this set up. We've set up our calculator to do this before, so unless somebody's changed some setting in your calculator, it should still be set up. If you go into your table, which is second graph, you should be able to enter the blue values that we identified, 0.5, 2, 4, and 6. And remember, we don't care what number we get. Our concern is, what's the sign? Did I get a positive or did I get a negative? Okay. If your calculator doesn't have this table feature or you're working with something that's just a scientific calculator, you're just entering these in by hand, within your calculator. So you're just going to take like the 0.5 and you're going to put in -2 cosine of 0.5, sine of 0.5 plus sine of 0.5. Okay, so you're just going to enter it in from left to right with 0.5 where the x is or the 2 where the x is or so forth. All right, so at 0.5, do you get a positive or a negative value when you plug it into the derivative?
Negative.
Mine says positive. Did I miss something? I have negative. Let me see. Sorry. Oh, I left my 2 off. That's what's missing. That will explain it. Oops. Yep, negative. There we go. Thank you so much. Leave off a 2 and things go wrong. All right, so I have a negative. How about when you plug in the number 2? What do you get? Positive or negative?
Positive.
It's positive? Okay, so trig functions often oscillate, but they don't have to. So you cannot just go, oh, look, it was a negative. Now it's going to go positive, negative. It might, but it might not. So don't go assuming something that may not happen. Depends on the function. What is the next value when we put in 4, positive or negative? It is negative, and the last one is positive. So this one is oscillating. It certainly would not have to, though, right? Especially because notice we squared cosine. It's cosine squared minus cosine at the beginning, right? This is not a function that would necessarily have to just go up and down at regular interval kind of things. Okay, now the question specifically at the beginning asked us to identify where it's increasing, decreasing, right? That's what the negative and the positive tells us. What does negative tell us that the graph is doing? It's decreasing, right? A negative derivative means that the graph, the original graph, is decreasing. And a positive derivative means the original graph is increasing. So we're going to write down our intervals where this is increasing and decreasing. So it starts decreasing, so I'm going to list that one first. So it's decreasing, not from negative infinity to something. We did that last time. We have to start with the end point that we were given, which is 0. And where does it stop decreasing initially? Pi thirds. So it's decreasing from 0 to pi thirds. We put a union symbol. And where also is it decreasing? Picks back up at pi, right? Until 5 pi over 3. And then we have locations where it's increasing. Where is it increasing? Good, pi over 3 to pi. And then I do a union and 5 pi over 3 to 2 pi. This is a really good example of a place that your calculator is not going to be super helpful in finding each of these locations. Pi over 3 is not a rational number. You can't just zoom in and get close and close and close with trace and figure out for sure exactly that it's pi over 3, right? You can't. It's not possible with your calculator. You could guesstimate it, and you might be close. You might even guess it right, but it would not be finding it exactly for you. All right, any questions on that one? Okay, let's take a look at some different directions. These directions are quite similar in the sense that they ask us to find the critical numbers, find places where it's increasing and decreasing. But C and D are different. C says that it wants us to use the first derivative test to identify the relative extrema. We've talked about that, but we haven't done it yet. And D, we're actually going to graph the thing when we're done to make sure that what we found makes sense. Okay, we're going to confirm it visually when we're done. Now, this is a pretty straightforward equation to do this with. Agreed? What's this a graph of? It's a parabola, right? A quadratic or a parabola. It's going to look like a U shape. Is it opening up or down? Can you tell? Down. It's opening down because the x squared at the beginning has a negative in front of its 2, right? It's a negative. So this is going to be a parabola opening down. So our basic shape, our expectation is look like that, right? It's going to be increasing, and then it's going to be decreasing after that. Okay? So I'm not using this as an example that's supposed to be complicated. I'm using this as an example to show you that what you expect to have happen, right, from what you know about this graph, is really going to play out with the calculus that I'm trying to show you really finds these things. Okay? So the first thing we do every single time we're looking for extrema or increasing, decreasing like we have been is we take the derivative. So what is the derivative of negative 2x squared plus 4x plus 3? Right. Everybody good at that? Okay, not a hard derivative, right? Agreed. So that's sort of step 1, if I'm looking at this list of steps. Step 2 is to find out where it's equal to 0. This is one of those cases where there is x in only one location. So we are going to isolate the x as we solve for this. So this is negative 4x equals negative 4. And if I divide, what's x going to equal? 1. Okay, there's only one critical point. It's not a very exciting process that we've gone through. So step 3 then is to put that critical number, and there's only one of them, on the number line. So we're going to do a number line. We're going to put a 1 on it. And then step 4 is to test values that are on either side of this 1. There's nothing in between anything this time because I don't have 2 values. But test values on either side of 1. You can test any values you wish. So if you want to test something crazy, feel free to do so. I usually test things that are pretty close to the value I'm looking at that are easy. So what's a value before 1 that would be nice to test? 0. And how about after 1? 2. Those are what I'd test. Now, this one's not real hard to plug in, so you can use your calculator if you want, but my equation's not difficult, right? The equation is negative 4x plus 4. So if I put 0 into negative 4x plus 4, do I get a positive or a negative? I get a positive, right? 0 is going to zero this piece out. I'm just going to get a 4. So this is positive. How about if I put in 2? Negative 4 times 2 plus 4. That one's negative. Okay, everybody good? So this one's not hard to just eyeball it. You're going to waste time probably if you use your calculator, but if you feel more comfortable, your calculator's there and you can use it. Okay, so that's not a problem. Okay, so what is positive telling us about this graph? It's increasing, right? It's going up. And negative tells us it's decreasing. But that's what we expected, right? That's the little graph I kind of threw in there on the side over there. We expected that, and we've confirmed that it really did that now, right? So on B, it says find the intervals where it's increasing, decreasing. We can do that now. It's increasing, and then it's decreasing. Where is it increasing? So it's increasing over here. There we go. It starts at negative infinity, or quote unquote, it goes all the way to negative infinity. And where will it stop increasing? At 1. Yeah, don't be misled by the 0. We tested the number 0, but the interval went all the way to 1. Okay? And then where is it decreasing? 1 to infinity. And do note, again, I mentioned this last time, and I'll mention it again, they're parentheses on the endpoints of everything, right? We're not increasing or decreasing at a point. It's always on an interval. The intervals are open intervals, okay? That's B. C says apply the first derivative test to identify if it's got a relative extrema. So what that means is what happened right here? What happened when it changed or when it hit that critical point? What do I have? Well, there looks like a jump in my graph because I've drawn these pieces in. There's not a jump though.
Relative maximum.
There's a relative maximum. So even though it's not connected, it really is, right? This is happening here. There's a maximum spot right there. It's the same thing that's happening, in fact, a more accurate description of what's happening right here. It's a maximum. So we have a maximum, but our maximum occurs at a point. A point has an x value and a y value. And right now, all I know is the x value. It's 1, because I used it on my sign chart over here, right? How can I find the y value that goes with the 1? Plug it into what, Elijah? Do you know? The original function. Exactly. So I take the number 1 and I put it into this equation, the original equation, not the derivative. If I put it in the derivative, I'm going to get 0. I mean, that's where it came from to begin with. If I put it into the original function, I will be able to find out what the corresponding y value is. Now, we're going to be graphing this in a moment anyway. So go ahead and put the original equation into your y1 value. So negative 2x squared plus 4x and plus 3. Now, obviously, this plugging in the number 1 into that is not a terribly difficult task. We could do that, and we should be able to eyeball it almost anyway. But in general, they're not going to be so nice and pretty, and you might want to put them in your calculator to find that value. And if you did, you could use your table to do so. Your table would tell you the corresponding value at x equal to 1 when you put it in. Mine says 5. Does yours say 5? Yeah. So my y value here is 5. So this is like step C. This one's B. All this above here was A. Okay, so we're going to graph this now. I mean, we've plugged it into the calculator for that point anyway, for part D. We know approximately what it's supposed to look like. I've kind of sketched a piece up there in their corner. And if you just do a zoom 6, it's probably going to be good enough. So I'm going to do zoom 6. It looks great. My graph looks something like this. Ish. Y'all good with that? And this is the point 1 with a y value height of 5. Does it look like that it has a maximum at 1, 5? Yes. Does it look like it's increasing from negative infinity to 1? Yes. Does it look like it's decreasing from 1 to infinity? Yes. Okay, so it's a visual confirmation that what we did made sense. Okay, the next one's a little more interesting because the function's a little more interesting. So there's a parabola just to give us the idea that our intuitive perspective really matched out with what we're doing. You may not be quite as familiar with this graph. You might have seen it before. X to the 1/3 plus 1. What's another way of writing x to the 1/3 that you might be more familiar with the graph for? You still might not like it, but
Cube root.
a cube root. So you might have seen this written before and talked about as a cube root graph. Sometimes curriculum will use the cube root of x as one of our basic functions, kind of like, you should know what x squared looks like. It's a parabola. You should know what x cubed looks like. You should know what the square root of x looks like. You know the absolute value of it. Sometimes cube root of x is included in that. Not always, but sometimes. The basic graph of x cubed looks like this. I'm sorry, this is what I want to draw first. The basic graph of x cubed looks like this, and then when you draw it with the cube root of x, it looks like it's laying down on its side. Okay? So we're looking at a graph that's sort of going to look like it's laying down on its side. The plus 1 is going to shift something up 1 because it's plus 1 on the outside. We're going to give a shift up. Okay? So that's sort of intuitively what the picture should look like. We're going to graph it at the end. If you wanted to graph it now, you could do that too. But we're still going to go through all the same steps we did before, finding critical numbers, increasing and decreasing from a number line, and the first derivative test. So let's get started on those pieces. So the first thing to do is to take the derivative. Now, the derivative is easiest to take in the original form it was given to us in, x to the 1/3 plus 1. So what's the derivative of x to the 1/3? I'll start. 1/3. What's next? Yeah, negative 2/3. What's the derivative of the plus 1? 0. Yeah, I don't need that part for the derivative. I mean, its derivative is 0, I should say that way. So I'm supposed to now look at this and decide where it's equal to 0 or does not exist. But the form that it's in with a negative exponent is not particularly friendly to sort of process. So I'm going to make some changes to this, not because I have to, in the sense that the problem started out looking like something different, but in the sense that it's easier to work with. So negative exponents, if I move them back to the denominator, will be positive, right? If I switch them. So I can move the 2/3 down to the x to the 2/3 to the denominator. So one step might be that I rewrite it like this. But again, 2/3 as an exponent is not a particularly friendly way to have that rewritten. So you might also consider writing it as the cube root of x squared. Okay. Somewhere along the way here, I want to figure out but where this is equal to 0 or does not exist. Now, the x is only in the denominator, right? I don't have any variables in the numerator. So I've got the number 1 on top, and I've got some other number on bottom. And I cannot divide the number 1 by anything and get 0. Y'all with me? If I have one cookie and I'm dividing it among a bunch of people, I can split it into tiny little slivers, but it never is nothing, right? So this will never equal 0. It just can't. I can't take something on top that's a constant, which I have as 1, and divide it by something and get back 0. However, I can have this not equal, I can have this to be does not exist. What value for x would make this equation does not exist? Yeah, if x is 0, I would get a 0 in the denominator, right? So this does not exist here will happen when x is equal to 0. So I do have a critical point. It's just not a critical point where the function is equal to 0. It's where the function doesn't exist. So setting this equal to 0, or setting this equal to 0 didn't give me anything, but does not exist did. Sorry, that was supposed to be this. So I only have one critical point. It's right here at 0. And I need to test numbers on either side. So if I've got 0, what number might you want to test before 0? -1. After 0? 1. That'd be great. You can put this in your calculator to test them if you wish, but because I'm choosing numbers that are 1 and -1, they're very easy to work with. So if I put -1 in for x, I would have -1 squared. What's -1 squared? 1. What's the cube root of 1? 1. What's 1 times 3? 3. So I have about 1 over 3. It's a positive value. In particular, when I squared the negative, it became positive. And the same thing happens with the number 1. 1 squared is 1. Cube root of 1 is 1. 3 times 1 is 3. I don't have any negatives. This is positive as well. So this one was step A. Where is this function? I shouldn't say it that way. What is this function doing before 0? What is that positive there telling us is happening? It's increasing. And after 0? Increasing. Now, you cannot just say that this is increasing everywhere because it's not increasing at 0. But this is increasing from -infinity to 0 and then 0 to infinity. It doesn't increase at 0 itself. But it's increasing all the way to 0 and then it stops briefly and then it picks back up to being increasing. What does that tell you about extrema? What's happening if it's going from increasing to increasing? There's no extrema, right? That's exactly what it tells us. There is no relative extrema. And let's go ahead and graph it real quick because that is part of our directions anyway. But we can confirm what we're expecting. Remember, we're graphing the original function, x to the 1/3, or you can graph cube root of x. If you're putting it in your calculator, you may have to tell your calculator the 1/3 in parentheses. Mine requires that, but not all operating systems do. And if we graph this, it looks something like this. It's not a perfect graph, but it's not too bad. Can you see how it's increasing until you get to 0, and it's also increasing after 0? Can you see that there's no relative extrema? Do you know what's happening at 0? There's a vertical tangent line. We talked once upon a time, it's been a while now, back in chapter 2, about the locations when derivatives don't exist. And one of the locations is when we have a vertical tangent line, and we don't see it real often. This is unique. It does not occur frequently. This has a vertical tangent line on the y-axis. If I were to draw a tangent line there, it would mirror the y-axis, match up perfectly. There's a vertical tangent in there. Okay. We're going to try to get done with the next one. If we don't quite, then I'll pause, finish, and then you guys can come back and watch it. But directions are actually all still the same here. They're phrased a little bit differently, but we're doing all the same thing. We're finding where it's increasing and decreasing, deciding relative extrema and graphing. Okay. This one is a mix in terms of it being an algebra and trig function at the same time. It's got components of both. All the components we do the same way. We're doing the derivative. So what's the derivative of x? 1. How about the derivative of 2 sine x? 2 cosine x. And we're going to set it equal to 0. So this is 2 cosine of x is equal to negative 1, or cosine of x is equal to negative 1/2. And notice they don't give us any, sorry, that was an accident. They don't give us any like end points, right? So they don't tell us what happens like if we go from the oh, they do. There it is. It's like I thought they did. It's up here in the directions. There we go. My end points go from 0 to 2 pi. Okay. So my interval, when I create it, will have 0 on one side and 2 pi on the other. I need to still find the x values where cosine of x is equal to 1/2. So thinking unit circle, right? We did a very similar one to this one earlier, except we did it to equal to positive 1/2, right? So if we're looking for negative 1/2, we're in quadrants 2 or 3, agreed? And we're still at pi over 3 values, which means I need to be up here and down here. What pi over 3 value am I at right here? It is 2 pi over 3. And what am I at all the way down here? It is 4 pi over 3. Okay, so this is at 2 pi over 3 and 4 pi over 3, at least on the interval from 0 to 2 pi. We can do the same thing that we did before in terms of finding nice values of what approximately the 2 pi over 3 and the 4 pi over 3 are equal to. So if I do 2 pi over 3, hang on, I get about 2. This is almost exactly 2. And if I do 4 pi over 3, it's almost exactly 4. It's not exact, but it's close. So I can test values in between these. So I can test the number 1 here, 3 here, 5 here. Those are working just fine for me. And I can do it in the calculator with the derivative. So if I put the derivative in, I have 1 plus 2 cosine of x. I can test my values at 1, 3, and 5. I have positive, negative, positive. Yep, those are my values. So I can see quickly that it's increasing, decreasing, increasing, right? So this is increasing from, 0 to 2 pi over 3, and it picks back up at 4 pi over 3 to 2 pi. And it's decreasing at 2 pi over 3 to 4 pi over 3. Now I'm going to push pause here and finish this up, but let me write this down first. I do have maxes and mins, yes? Right here I have a max, and right here I have a min. So those two locations are the maxes and mins that I'm asked to find in the part B here. I just need to find the corresponding y value that goes with it and graph it. Okay, so I'm going to push pause. I'm going to let you guys leave. There's probably 2 minutes left, and then you'll be able to watch those last 2 minutes, okay? All right, so the conclusion of what we were doing today, we have two locations for our relative extrema. I need a little bit more space. Let me move this, actually, make it smaller. So all of this was part A, everything we've done so far. Part B is actually the maxes and mins. So at 2 pi over 3 and at 4 pi over 3, I have one of each, right? And so in particular, 2 pi over 3 is the max and the 4 pi over 3 is the min. And if we plug those into the original function, it doesn't work very well to put them in the calculator. And the reason it doesn't is because I'm dealing with trig functions and I'm going to get some square root of 3's over 2's. So if I put in 2 pi over 3, 2 pi over 3 goes in for x. Let me shift this over a little bit so I have some more space. And so I end up with 2 pi over 3, but then putting the 2 pi over 3 in for the x in the sign actually ends up giving me a square root 3 value. So I end up getting that this is going to be plus the square root of 3 over 2. And then, so that's the way you get it exact. If you use a decimal approximation, that's an approximation. We want an exact answers when at all possible. Same thing if I put in 4 pi over 3. I'm sorry, these are kind of cramped in here a little bit, but I do 4 pi over 3, and then I'm going to end up getting a negative square root of 3 over 2. Correction, sorry, each of these were multiplied by the 2 in front of the sign, and I won't have the over 2 part because I'll be multiplying it out. Okay, so they're plus square root of 3 over 2 and then minus square root of 3. Plus square root of 3 and minus square root of 3. Okay, so that's the max and the min. And then if you graph it, it looks, again, I'm running out of space again. Let's try one more time. Okay, if you graph it, again, from 0 to 2 pi, it looks something like this. Sorry, I don't really need that much space below the graph, but I have it nonetheless, I suppose. It looks like this. Kind of looks like a sine graph, sort of on an angle. So over here is my 2 pi over 3, and right here is my 4 pi over 3. So you can see that you have the maximum occurring right there and the minimum occurring right there. And you can verify that it's approximately at the right y values. If you want to sort of sketch over there and change your values into approximations, you can see those values too.